Hello, and welcome to The Conversation. I am Space Mike, and I am joined today by our resident astronomer, Jared Head, and we also borrowed our own Lisa from the Tomorrow Science Show. Thank you very much for being here. We have a very exciting show for you today. In fact, coming up in news, we have...
Virgin Galactic rockets ahead with testing!
And an inhospitable place may actually be hospitable after all.
Awesome, awesome. We're also going to be joined later on by Paddy Neumamm from Neumann Space. That's going to be our interview today. But of course, I want to give a huge shout out to Dutta and the Higginbothams for producing the show. So thank you very much. Today is going to be an awesome show. This is Tomorrow Orbit 11.14.
Good morning. How's everything up in the sky?
Before we get started with today's show, we want to give a huge shout out to our Escape Velocity citizens who have been contributing $10 per episode on Patreon or $30 a month on makersupport.com. Not only do these folks get their name in the show during all three segments, they also get access to our exclusive citizen-only hangouts, they get early access to our view-only copy of the show rundown, they get free worldwide shipping to the Tomorrow swag store, and they also get a read-only access to our host channel, which is going to be a future reward very soon. So if you would like to find out about those rewards and all the other benefits available, please visit us at our makersupport.com or patreon.com/TMRO. All right, we have some really exciting news, but first we actually want to get started off on some launches, as we always do. But I'm going to take a little break from this, and we're going to talk about some really cool ones instead. So Lisa, first off, tell us what the first launch happened last week.
I'm so excited to be doing launches this week. It's so much fun. So we had a SpaceX launch, and it was the CRS-14 mission. It occurred on April 2, start at 2030 UTC, from the Space Launch Complex 40 at Cape Canaveral Air Force Station in Florida.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition.
So Dragon had 2,630 kilograms of cargo and supplies, including experimental supplies, like the marrow experiment that we talked to the principal investigator of, Guy Trudell, in the last Tomorrow Science episode, Discovery 1.04, so go check that out. This flight also reused the booster from the CRS-12 mission and the Dragon pressure vessel from CRS-8. There was a successful stage separation and deploy of the Dragon spacecraft, but there was no landing attempt on this particular flight. They did a hard landing in the Atlantic Ocean to gather data on the limits of booster re-entry. And it was also a berthing that occurred to the International Space Station, and this berthing occurred on April 4 at 10:40 UTC. Dragon's going to stay at the International Space Station for about 1 month, and they're going to reload it with some more experimental materials, things that have to come back down to Earth, and even some trash, and then it's going to splash down in the Pacific Ocean. Now, the cool thing about this launch is that the webcast didn't stop at 9 minutes. Woohoo! So apparently, NOAA licensing is not required for government missions, according to Tahara Dawkins at the NOAA, or National Oceanic Administration. Is that the
Oceanic and Atmospheric
there we go. Thank you.
Administration.
Yeah, it's a tough one.
Yeah. We
Yeah.
don't have something like that in Australia. So Tahara Dawkins from NOAA, as Commercial Remote Sensing Regulatory Affairs Office, said that if it's a government mission, you don't actually need to have that required NOAA license. So I believe the next mission coming up for SpaceX is also a government mission, so looks like they'll have a fantastic webcast for that. And who knows if SpaceX and NOAA are going to sort out their licensing issues. I hope they do, because I hope to see many more amazing SpaceX webcasts.
Well, I don't know about you guys, but something that I'd seen is that they were going to try to expedite those type of licenses in the future. So hopefully we won't have problems like that again. But with that particular launch the week prior, I guess there wasn't enough time. Like, these are some new regulations and stuff like that, and there wasn't just just wasn't enough time for that license to be granted. So hopefully there won't be problems like that again in the future. But there was another launch last week as well.
There was indeed. There was an Ariane space launch of an Ariane 5 rocket that occurred on April 5th at 21:34 UTC from the Guyana Space Center in French Guiana. Let's check it out.
6, 5, 4, 3, 2, 1, top. Allumage du Vulcain. Allumage des EAP, décollage.
Now, this launch was carrying a dual payload. It was the Superbird, or also known as DSN-1 satellite, and the Hylas 4 satellite. It was delivered to a geostationary transfer orbit of 250 kilometers by 35,786 kilometers. The spacecraft will use their onboard thrusters to circularize their orbit, and they're expected to have about a 15-year operational lifetime. Now, Superbird 8 carries Ku and Ka band transponders to provide communications services for the Japanese company Sky Perfect JSAT. Hylas 4 will provide Ka band services throughout Europe and is operated by the British company Avanti Communications. This is the 98th flight of the Ariane 5 rocket and the 242nd flight of any Ariane class rocket. So nice job, Ariane Space.
Yeah, and especially after the previous Ariane 5 launch where they had a little bit of a trajectory glitch.
Seems like they've sorted that out for now.
Yeah,
so
glad to see that.
good.
Yeah, they're back on it. So,
well, awesome. Thank you for giving us that update on the launches that occurred last week. But let's go ahead and get into some news. There was some really interesting stuff that has happened this week. But first, I wanted to start with you, Jared. Tell us what is going on with this. There is what's going to be happening with this whole exoplanet hunting?
yes, so not only are we going to get TESS, the terrestrial exoplanet, or transiting exoplanet survey satellite coming up in a couple weeks, which is the next SpaceX launch, which I'm so looking forward to because it's going to give us so much data. Also, you know, we sort of had folks say that we didn't really look at the European Space Agency stuff enough, so I decided to go in and take a look. And it turns out this week they approved a British-led mission to move on for its expected launch in the mid-2020s. And this mission is called the Atmospheric Remote Sensing Infrared Exoplanet Large Survey Mission. That's a backronym, also called Ariel, and it will be the 4th mission flown as a part of the European Space Agency's Cosmic Vision Plan. Now, Ariel will use a mirror about 1 meter in size, and it won't actually be looking for exoplanets itself, but it will be using a near-infrared spectrometer to measure the chemical makeup of existing exoplanets. Now, the light from over 1,000 exoplanet atmospheres will be broken up to find the fingerprints of their makeup using absorption spectrometry. So, looking for specific wavelengths of light absorbed by specific elements and molecules. And we look for these dark lines in the pattern of light, and we're able to identify very precisely what the compounds or elements are present. So when you look at the spectral data, this is kind of what you see on the screen right here. So here's a nice graph for you all to take a look at what that data is going to be like. Now, Ariel will be launched in the late 2020s by an Ariane 6 into a halo orbit around L2, Lagrangian point 2. And this mission,
Earth and Sun? Between Earth and Sun?
Yeah, Earth, Sun, L2. So,
okay.
Yeah, thank you for specifying, Space Mike. That's very important. The mission is planned for 4 years, and Ariel will take multiple looks at the same exoplanets to see if things change, which could indicate seasonal and potentially even daily changes in the atmospheric makeup. And although potentially habitable exoplanets will be studied, the overall goal is to characterize a multitude of planets. So we're not just looking at planets that could potentially be Earth-like in the habitable zone. They want to look at all of the exoplanets and really be able to compare their atmospheres and their potential chemical makeups with each other. So, very cool mission. So,
because we can only find out so much about their chemical makeup from the light spectrosity and everything like that. This will be able to really tell us what their flavors are, whether it be the gas giants or Earth-like planets, and what they might actually be made of. So this is actually really exciting.
Yeah, and there's been a lot of speculation of late talking about potential like Earth-like planets with super thick atmospheres and things like that, and also gas giants with super thin atmospheres as well. So this is sort of really going to begin to not just talk about masses and sizes and densities and orbits and expected temperatures. Like, we'll actually start to get like the meat and potatoes of what this exoplanet may potentially be made out of, and more specifically what that atmosphere is like. And from that, if you find things in the atmosphere, you could potentially discover not just a habitable place, but maybe a habited place. So, which is
super cool.
Like wild to think about. So.
That's why we're doing this, right?
Exactly.
That's what we want to find. But yeah, if we get our favorite chemicals, get a little bit of H2O and some nitrogen and stuff, that might, even if we don't find anything, that might be some future destinations for us in the far future.
Well, as we say in science, even finding out you're wrong is a result.
Yeah.
So,
Definitely.
Yeah, definitely.
Yeah.
Well, let's move along. There was a really exciting rocket test this week. Lisa, tell us what happened.
There sure was. I was going to add this as a launch, but it's not technically a launch. It's more of kind of a test, so I put it as a separate news item. So, on April 5th at 15:02 UTC, the aircraft carrier VMS Eve lifted the VSS Unity into the sky over Mojave, California. Let's check it out.
Now, this has happened before, though. They've done a bunch of glide tests. What was special about this one?
This one was special because they actually turned on the engine. So the carrier aircraft climbed to 46,500 feet, and the VSS Unity was released, lighting her nitrous oxide HTPB, or hydroxyl terminated polybutadiene, compound hybrid rocket motor a few seconds later. They had a 30-second burn, and they reached Mach 1.87. It's the first time the VSS Unity has gone supersonic. They did an 80-degree climb and then coasted to an apogee of 84,271 feet, or for those using the correct metric system, 25.6 kilometers. Then they activated their feathering mechanism for re-entry, and this time they actually had additional safety mechanisms for that feathering system, because that is the system that caused the fatal accident that they had previously. Then they had a safe touchdown at the Mojave airstrip, and the Unity itself was piloted by Mark Stuckey and Dave McKay, and the VMS carrier aircraft Eve was piloted by Mike Masuki and Nicola Pisa.
Wow. And what awesome footage. I think that might, I don't know if that's the highest altitude that they've ever received, but I think that's the first time I've seen footage of that where you could actually see black sky and curvature of the Earth. And
definitely with the
so.
VSS Unity. The Enterprise had been to that level before and had that kind of footage, but for the Unity, this was the first time. So, they're well on their way to finishing their test program, and hopefully they might be able to get humans on board sometime soon. So,
wow.
All the best.
Do you think they're actually 6 months away this time? Or?
No.
I'm not sure. We'll see.
I would say no. You could really tell that Virgin Galactic is doing all the right things after their testing accident
Slow and
from
steady,
2014.
make sure they've got it right.
Yeah, and they're and that's hats off to them for doing that too, because it's so important for safety.
Definitely.
So,
absolutely, absolutely. Now let's go ahead and move on though, because this is really exciting. But we want to, we're just going to have to wait and see what progress happens with Virgin Galactic. But there's some new information out that a place that we know of as being pretty hospitable might actually have some possibilities. Where?
Yeah.
This blows my mind.
Yeah, this blows my mind too, especially because this was just the study kind of came in under the radar, and then all of a sudden everyone was looking at it because it's so cool. We've often thought that the hunt for life in the universe may not require us to actually leave our own solar system. A lot of folks have pointed to Mars, and then recently they've pointed at the moons of Jupiter like Europa and Ganymede and potentially Callisto, and also the moons of Saturn like Enceladus and Titan as well. But a study by a group at the University of Wisconsin-Madison's Space Science and Engineering Center has opened up a possibility for a place often thought to be completely inhospitable and hostile in every respect to life. And that would be Venus.
Our next door neighbor.
Yeah, one of our next door, our Earth's evil twin, if you will, in the solar system. So Venus's surface absolutely lifeless. We can barely engineer systems that can survive there for longer than an hour at a time. And that's because the pressures there are 90 times that of our atmosphere and at temperatures of 450 degrees Celsius. But models suggest that Venus wasn't always this way, that it likely had water like the Earth, and that water may have actually been present on the surface for about 1 billion years. Now, very surprisingly, Venus has a place where life could potentially exist, and it's in its atmosphere, specifically 40 to 60 kilometers above the surface. This is an altitude that multiple probes flown into Venus's atmosphere in the 1960s and 70s have found temperatures and pressures similar to what life works well with here on Earth. And here on Earth, we've actually found microorganisms alive at altitudes as high as 41 kilometers above our surface. We also have life here on Earth that can thrive on carbon dioxide and generate sulfuric acid. And Venus's clouds also show those periodic dark patches, which are more prominent in ultraviolet light, like images from the JAXA probe there, which you probably know.
Akatsuki.
Yes, excellent. Akatsuki. Now, Venus's clouds, they show those dark patches and they can hang around for days. Now, no spacecraft has been sent to Venus that has carried instrumentation that can distinguish between organic and inorganic products. But a mission is currently being proposed right now called the Venus Atmospheric Maneuverable Platform, or VAMP. Now, flying like an airplane, but also floating like a blimp, it could be within Venus's atmosphere for almost a year, sampling and hunting for potential Venusian microorganisms. And cool fact that I learned in studying for this story is that our atmosphere that we have here on Earth, just nitrogen, oxygen, is a lifting gas. It's a great lifting gas for the atmosphere of Venus. So that's like, I never even thought about that.
So you just put regular air in and you're fine.
Yeah, you don't have to bring helium if you do like a crewed mission to Venus in the clouds. You just have your atmosphere there.
And it's my understanding, too, that the carbon dioxide below this level that we're talking about is just about the same density as water, right?
Yeah,
it's essentially, I mean, at that level, I mean, it has that nice temperature right there, but the atmosphere becomes less dense at that level. So it just fills my brain with all these ideas of like cloud cities or flotillas that have just a bunch of plants just going crazy, eating up all of that carbon dioxide. So.
Yeah, and that was just like, it's one of those studies that like nobody really looked at until somebody actually looked at it. And then was like,
got rid of our assumptions. Like we assumed that Venus was inhospitable.
Yes.
But we didn't base those assumptions on anything. And now we've actually taken a look at it and looked at the data. Like,
yeah, it's just like what I always love to talk about in terms of assumptions, which is that we thought you have to have oceans exposed in order to have life, but we've found that there's life on Earth that can perform chemosynthesis. So no need for photosynthesis, just around hydrothermal vents here on Earth, which really opens up the possibility. And it turns out when we go out and we look for these ocean worlds, Earth with its directly exposed oceans is actually the weird one.
Yeah.
It's mostly covered up, encased ice or rock interacting oceans here in our solar system. It's like so wild, and you know, really, when it comes to life, we only understand what works here on Earth. As we like to say sometimes up at Griffith Observatory, life could be completely radically different, and we could actually be the weird life running on oxygen, you know, here in the universe. But we haven't found it yet, so we have to look for what we understand works as life. So, but there are like other possibilities. If you want to get into that, maybe we can do like a Tomorrow Sci-Pod or something about that.
Yeah,
but
I think that would be cool.
Yeah, it's pretty wild stuff. So
just exciting the possibilities that might be right here in our own neighborhood.
Yeah.
But in any case, though, we need to move on. We're going to take a little bit of a break, and then we're going to come back and have a really awesome interview with Paddy Neumamm, aka Patrick Neumann from Neumann Space, and we're going to be talking about a new type of ion thruster that might revolutionize the industry. So stay tuned for that. We'll be back in a little bit.
Look into her face, determination in her eyes. She won't give up or quit or fall for little fashion lies. Filled with awesome expectation, this girl's a fascination. And nothing in her way will keep her from her destination. Cause she's fire walking, she's fire walking. When it's hot, she keeps on moving, through the heat keeps on improving. Yeah, she's fire walking, she's fire walking to be free.
And welcome back to Tomorrow. Before we get started with our interview today, we wanted to give a huge shout out to our citizens of tomorrow. These are our Escape Velocity citizens who've been contributing $10 per episode on Patreon or $30 a month on makersupport.com. But we also have our Orbital citizens who've been contributing $5 per episode on Patreon or $15 a month on Maker Support. These folks get their name in the show during the second and third segments of the show. They get access to the citizen-only hangouts, early access to After Dark, as well as free worldwide shipping to the Tomorrow swag stores. They're also going to be getting voting rights on upcoming roundtable discussions. So be sure to check out all of the different benefits and rewards that are available. And thank you so much to the folks who have been contributing to make all of this possible. All right, so today we're going to have a really awesome interview. We are joined today by Dr. Patrick Neumann, aka Paddy Neumamm of Neumann Space. Thank you very much for joining us today.
No trouble at all. Thanks for having me.
Thank you. So first I wanted to start off a little bit with your history. How did you get involved with the space industry?
That's an interesting one. Like a lot of people involved in space, I started out pretty young. You go around and you talk to a lot of people, there'll be this one moment in their childhood where they can tie it back to. So people from of the right generation will start talking about watching the Apollo moon landings. For some, it was watching people do backflips on Skylab. For me, well, I was born in the mid-'80s. I was too young to remember Challenger, but I was really keen on dinosaurs at about the same time that Voyager 2 was about to do its flyby of Neptune. And after I read the bits in the back of the books about what happened to dinosaurs, the asteroidal impact theory was starting to become more and more popular at the time, I started reading up about space, and then I heard that Voyager was going to be doing its flyby. And I was that kind of kid that held their breath, stamped their foot, and carried on like a pork chop until my parents agreed to let me stay up to the ungodly hour of 10:30 at night to watch the live feed on a special edition of the ABC Australia, that is, TV show Quantum, which they had a live cross to NASA JPL as the data was coming down. And I can remember watching, grown-up nerds dancing with joy when Voyager 2 had passed behind the rings of Neptune, and they measured the dip in radio intensity. So that's where it kind of got started. And as I've learned more and more about it, figured that science and engineering was what I wanted to do with myself, applied myself at school, got good results in my end of high school exams, managed to get a scholarship to go to the University of Sydney to study aerospace engineering and physics. I'm originally from the hills outside of Perth in Western Australia. So I moved 4,000 kilometers. That's somewhere around 2,800 miles in the old money, I think, to go to uni, because it's where they taught what I wanted to learn in Australia. And was not the best undergraduate student. I've got this terrible problem of falling asleep in lectures. So I wound up doing as many practical projects and laboratory projects as I could get my hands on, and noticed something a little bit odd in a project I did when I was a third-year student. I was measuring electric field intensity and voltages in a certain type of plasma discharge. And with processing the data enough, looking at what is happening at what times, I could figure out what the average effective velocity of this plasma was. And I noticed that these titanium ions in the plasma were moving at about 23, 24 kilometers per second. And I figured you could probably make a rocket motor out of that, and that I need to have an honors project for my undergraduate thesis in a year or two after that. And that became my thesis. Measuring with thrust. Does it produce thrust? Can you measure it? Can it predict it? Is it linear? And everything else has built on from those results. Thankfully, I had a good honors thesis. It does produce thrust. It is nice and linear. Presenting results at a conference just after the game portal had come out, and managed to win a few drinks from the other postgraduate students by getting the line, "These points of data make a beautiful line," into my presentation multiple times. It was fantastic. And through master's and PhD, and now into commercialization and development.
So with this this technology that you've been studying, and you even describe it as almost like an idea that you almost inherited, what led you to the point where you did want to take this further and create your own company to promote this, which you're calling the Neumann Drive? And let's talk about what this is, because it is a type of ion engine, but it's a lot different than what most plasma-based ones are using. This one is using solid fuel and electricity to produce thrust, and you compare it a lot to like an arc welder. So can you explain to us in layman's terms how this works like an arc welder?
Sure, no worries. I'm going to take a little step back and have a chat about some of the other technologies first.
Okay.
There are two main types of flight-rated electric propulsion systems. There's the Hall effect thruster and the gridded ion thruster. And both of them work by getting a gaseous fuel, commonly xenon, ionizing it in a discharge chamber, and then accelerating the ions out the back end of the spacecraft to produce thrust forwards. The way they do that acceleration is different for each one. The gridded ion thruster has electrically charged grids that they accelerate the ions through. And this works pretty well. It's been used in space numerous times. People use it for station keeping, as well as propulsion to go from one orbit to another, or to go to distant destinations for exploration. An example of that would be the Dawn probe to the asteroid belt. A Hall effect thruster doesn't have the grids. Instead, it traps a bunch of electrons in a dense magnetic field and uses that as a virtual electrode, so that the ions get sucked out the back through this negative charge zone, and you don't have an electrical grid that gets eroded and worn away. Our system uses different physics to create its plasma. The gridded ion thrusters, the Hall effect thrusters, they use a gaseous fuel, and so they can do things like radio frequency resonance, microwave resonance, cyclotron resonance, all these various technical bits and pieces. Our system is different. We take a solid fuel, just like an arc welder, similar to an arc welder. We strike a plasma arc off it. If you've ever used an arc welder, well, arc welder is the Australian term for it. I believe the American
We call them arc welders here too. Yeah.
Oh, cool. I've also heard them referred to as stick welders sometimes. Mm-hmm. There's also TIG and MIG, which use different, slightly different physics for it, but they all work in kind of the same way, that you've got a positive part of your circuit, which is whatever you clamp the big, huge alligator jumper lead to, and that's the anode, that's the positive part of the circuit. You've also got the cathode, the negative part of the circuit, and with the arc welder, that's the long, skinny welding rod. And when you drop the mask down in front of your face to save yourself, because safety is important, you bring the tip of the welding rod close to the workpiece, and you get a very strong electric field between the tip of the welding rod and the workpiece, what the anode is clamped to. When the field gets strong enough, it can rip apart air molecules and start sending electrons down this ionized channel and complete the circuit. This causes a lot of heating at the tip of the welding rod and evaporates material from the welding rod, from the cathode, and that gets transferred through the plasma onto the anode and creates the weld. In a welder, the plasma is primarily made out of iron and carbon, because that's what the welding rod's made out of. In our system, we use a different geometry. It's currently up on the screen there. We have, this is it in cross-section. When we strike the arc, we can strike the arc off whatever material we want as the cathode, so long as it is solid and conducting. If you want to make a titanium plasma, you want to make an aluminium plasma, you want to make a cadmium plasma, simply put that material in as the cathode and away you go. We strike the arc differently in our system because we operate in a vacuum and we have a different geometry. Rather than bringing the cathode close to the anode and using a mechanical trigger, which some research groups do for materials deposition physics, we use an electrical flashover system. So the trigger pin is connected to a very short, sharp, high voltage source that creates a very short discharge across an insulating material over to the cathode to start the discharge. Once the discharge is started, We power the discharge by dumping a capacitor bank into the plasma, and that drives the rest of the discharge. When that particular pulse of plasma has gone on for long enough, we turn off the power from the capacitor bank, and the plasma stops.
Depending on what type of material that you're using for your cathode, does the amount of electricity required vary depending on what material that you're using?
A little, yes, and it's due to how good the material is at remaining solid. The technical term is lattice binding energy. It's the amount of energy that's holding all the atoms in the solid metal in their spot in the solid. Different materials require different amounts of energy to move atoms out of their lattice. Materials like magnesium and lithium are very easy to move the atoms around. Other materials like tungsten and tantalum require a lot more energy. This is reflected in the burning voltage or the running voltage while the arc is going. After you trigger the arc, you start short-circuiting a capacitor bank, but there's still a voltage difference between the cathode and the anode, and this is called the running voltage or burning voltage, depending on which research paper you're looking at. Typical burning voltage for magnesium can be 30 to 40 volts. A more typical burning voltage for tungsten can be, in a system with the same geometry, up to 80 to 100 volts. So the amount of voltage you need will change. The amount of power you put into it, well, that's an interesting question, because our system uses pulses. So you can have quite a low power system, slowly feeding power into the capacitor bank and gradually bringing the power up and then drop in a pulse, and then gradually bring it back up again, and then another pulse. So it depends on what you're doing and what power budget you have to determine how much power the system needs.
Well, there's quite a few questions that I want to get into, especially regarding the different materials that you're using. And I wanted to address some of the questions that are coming from our chat room as well. First, I wanted to ask from Rebel Ace Friesland, who asks in our chat room, what kind of power input and output are you aiming for?
Ooh, okay. Power input. At this point in time, we are looking at designing something for the small sat side of things.
Okay.
And making sure that our power system is fairly robust, modular. And we reckon that if we modularize it in the correct way, we'd be able to have a cut down version that's not going to be as efficient. That will still work well for a CubeSat side solution. And at the other end of the market, if you put a bunch of these operating in parallel, there's no reason why you couldn't have multiple kilowatts going through the system. The laboratory test stand I used at the University of Sydney for most of my research work was cannibalized from an old tokamak fusion reactor. That's where Australia did part of its fusion research for a number of years. Then it got moved into a materials physics research experiment. Then I inherited it, and the system will quite happily put a couple of kilowatts through a 25 millimeter cathode. So power input, yeah, you design it to handle what you give it. Power output, a bit hard to quantify, but the thrust to power ratio of a lot of the materials we're interested in using as fuels tend to hover between 10 and 25 micronewtons per watt. To put that in perspective, flight-rated ion thrusters tend to be in the 30 to 40 micronewtons per watt. Flight-rated Hall effect thrusters tend to be in the 50 to 55 micronewtons per watt range. However, they've had a lot of work done on them to optimize them, and this is a fairly new technology. There is still more work to be done.
So let's talk about the different materials then, the different sort of efficiency that you've been getting. A question from our very own Dutta is, do you get different amounts of thrust from different materials, and what materials have you tried? Which ones are the best?
All right, I'm going to go with what materials have I tried first.
Yeah.
So if you've got rather a lot of spare time, you can go onto the University of Sydney's website, and in the digital collections of the library, you can find the digitization of my PhD thesis. In there, you'll find a lot of needlessly dry technical prose, because that's how PhDs get written these days, and a large number of graphs detailing what I did and why I did it. And part of it will be why I chose the 11 different materials I chose. The reason why I chose those materials was I had a look through the literature and the experimental results of people doing a bunch of background research and finding materials that looked interesting. I wound up choosing 11 as representative samples of 3 different groups. There was a 4th group I wanted to test, and I'll get into that in a moment. The groups were light elements, because lighter elements have a higher charge to mass ratio, and so their ions would move a lot faster. And from the light elements, I chose carbon, aluminium, and magnesium. Refractory elements were also a class that I looked at, because they have a high melting point, so they wouldn't produce a lot of vapor, so the ions would be able to move with fewer collisions and be more efficient at producing thrust by using a fuel. From these, I chose titanium, vanadium, chromium, molybdenum, tantalum, and tungsten as a compromise between safety and cost. I asked for some quotes for some lab-grade hafnium and niobium, just for the hell of it. And it turns out that the amount of hafnium I wanted would have cost 1.5 years PhD stipend, and the amount of niobium 6 years PhD stipend. So that's not going to be on the cards. 3rd class was heavy non-refractory elements. I chose tin and bismuth to test. Others from that class included lead, antimony, and cadmium. So didn't want to do those. Kind of a bit toxic. When the system operates, it produces quite highly ionized plasma, but it also produces a little bit of dust, and that dust will be on the micrometer scale. So it'll go through most filters, and I didn't want to breathe in heavy metals. Which brings me to my 4th group, which were the actinides, because the paper I saw from the University of California, Berkeley, research group, that is, detailed a large number of experiments on a large number of elements, including uranium and thorium. Don't know how good their filters were. I hope they had really good filters. In fact, I'm pretty certain they did. And that they decontaminated their system quite well, because sure, uranium and thorium by themselves are alpha emitters, not particularly dangerous unless you breathe them in. And if there's dust around, well, you're going to breathe that in nice and easy. Didn't wind up choosing those 2 metals because we didn't have the safety equipment, and you'd probably need a license in Australia to have even depleted uranium or metallic thorium.
Sure. Now, what about superconductive metals like gold, or even superconductive metals that don't require extreme temperatures, like thallium, for example? Have you guys experimented with any of those type of materials? Or would that even work in this system?
Well, no, I don't think anyone's done any work on it on them while they've been superconductive. But they have been used in research for materials coatings. Similar to, you can use an arc welder to build up layers of material as you weld. You can use this system to grow thin films of one material onto some background substrate material. People use this all the time in industry as one of the machines to build thin coatings, such as the indium tin oxide on the inside of glass to make touchscreens into a thing, or bio-friendly coatings on hip replacements to make them more accepted by the body, less inflammation, shorter healing times, all these fine things. People have done work with gold, with platinum, palladium, with reactive atmospheres, with a bunch of different things, but not much work has been done using them as thrusters. To get back to some of the other questions from the person playing along at home, in terms of thrust, single-digit newtons during the pulse, but each pulse will deliver probably 0.5 to 1.5 millinewton seconds, depending upon the settings that you operate it under and what fuel you're using. So the amount of impulse is actually pretty low because the pulse is only a couple of hundred microseconds long. Imagine someone's tapping on a tabletop with a very small hammer, a little hammer you see in that the doctors supposedly use to test people's reflexes by hammering them on the tendons attached to the kneecap. Imagine someone tapping along with one of those, that sort of level of impulse and force.
And speaking of it as a thruster, there's so many questions coming from our chat room about, first off, from Hannes Vorbert from Twitch, how long would the fuel last compared to other ion thrusters? And one of our other Cramped Eyes says, what are the pros and cons of this versus other ion engines? So how could you use a system like this? Because other more traditional, the Hall thrusters or reaction have extremely low thrust. So how does this compare?
This one also has quite low thrust as time average thrust. During the pulse, yes, it's hammering along, it's tapping along quite happily, but it's only on for a short amount of time, and then the capacitor bank needs to recharge, and then you can pulse again. The thrust levels are comparable. The thrust to power ratios they're close, they're within the same ballpark. As for fuel usage rates and where you can go with this, that depends on a different efficiency metric, the specific impulse of the system. Mm-hmm. Specific impulse is kind of like miles per gallon for spaceships. It's how much momentum change you get for a given weight of fuel. If you do the derivation, it turns out to have units of time, and so we give a number in seconds for this. A Hall effect thruster, a well-behaved flight-rated system you can buy off the shelf from Busek or Fekel or Snecma. That'll do you maybe 1,800 seconds at peak. You can buy the ZIPS 25, the Xenon Ion Propulsion System, 25 centimeter diameter from L3 Technologies. They'll do you about 3,500 seconds at peak. With magnesium in our system, under the right conditions, we have demonstrated thrust in the lab at over 11,000 seconds of specific impulse. Less fuel-efficient materials such as titanium, vanadium, carbon, and molybdenum have demonstrated specific impulses in the 4,000 to 5,000 second range. If you to internalize this, you can. If you want to do station keeping to keep a large communication satellite in geosynchronous orbit, you need to have your little rockets on it to give it that little push every now and again to keep it in the right spot so your ground station can talk to it. Currently, this is done by either chemical rockets or, in some cases, Hall effect or gridded ion thrusters. They all need fuel to operate, and the more efficient your thruster is, the less fuel it needs to do the same station keeping maneuvers, which means for a given mass of fuel, you can operate for a longer time. With a magnesium fueled system operating at 10,000 seconds, it would require about 100 grams of fuel, so about the size of a king-sized chocolate bar, to keep a 3 to 4 ton communication satellite in the correct orbit, and that's a chocolate bar a month.
Wow.
A bit more than a kilo a year, 2-3 pound.
Yeah, with that amount of efficiency. So let's talk about other applications then. I mean, yes, that would be great for station keeping and even having geosynchronous satellites and have that station keeping that you need for many, many years. But what are some of the other applications that you would like to see this be used for?
There's a bunch. There are a lot of missions that people have been wanting to do, and a lot of applications people have been wanting to do that are highly limited by efficiency. One of those is space tugs. There's a lot of talk and a lot of planning currently going on for satellite lifespan extension and satellite servicing missions, so that you can get a little bit more lifetime out of your old communication satellites, for example. If you want to do multiple missions of these, you're going to need a really efficient thruster to get around. If you want to do high-powered tug operations, such as you launch a large module or a large satellite into low Earth orbit, and you want to push it up to geosynchronous Earth orbit, or take it off to somewhere else, such as for one of the several plans that are out there for NASA in the next couple of decades. Several of them involve lunar orbiting stations or out at the Earth-Moon Lagrange points. You're going to need something with a whole lot of efficiency or a whole lot of grunt to be able to move your modules up there. If you want to go the efficiency route, you're going to need a highly efficient system. We've run some numbers on orbit-raising tugs and generalizing this orbit-raising tug using molybdenum fuel at 5,000 seconds of specific impulse. We chose molybdenum because it has a higher thrust-to-power ratio, and thus it would be able to get more thrust for the amount of power we're putting into it and do a faster orbit transfer. With this, we can do 1-ton tug, dry mass tug, moving a 4-ton ComSat from low Earth orbit to geosynchronous orbit, and then coming back for the next load because it's a tug and you want to be able to use it again. This would require about 650 kilograms of molybdenum fuel. It would require about 330 days for the complete mission evolution. And the amount of solar power you need to be able to do this is within the realm of the possible. It's about 65 kilowatt electric being delivered to the thruster array, which is within the realm of the possible according to a number of design studies we've seen that people have presented at conferences discussing high-powered tug concepts. If you use this same tug concept, you can then load it up with more fuel because molybdenum is dense. Molybdenum has a density of about 10.8 grams per cubic centimeter, so 10.8 times the density of water. It's fairly cheap. You can buy scrap molybdenum at 99.9% purity for about 20 US a kilo.
Oh, wow.
Which beats the tar out of aerospace grade xenon at about 1,200 US a kilo if you buy it in bulk.
And molybdenum is your most fastest fuel, right? Or is
yeah.
it the most? Is that the most that you've gotten, like, measured the most amount of thrust out of?
No, that's actually tin.
Oh.
But the problem with tin is it's a very low melting point material, so its efficiency is crap compared to the others. Best I've got is about 620, 630 seconds of specific impulse, which is pretty good if you're comparing it to chemical thrusters. But if you're looking at electrical propulsion systems, you've accepted the fact that you're not going to have the very short transfer times you can get with a chemical system, and you're looking for efficiency in this case.
Yeah. Now, there's a couple of questions from the chat room that are that I'm also wondering about that are related. From YouTube, from Kristen Bard asks, is there a risk of this engine signaling excessive electromagnetic interference possible for itself and maybe even other satellites? And related to that, also coming from Vax Headroom in our chat room, he says, aren't you creating a cloud of ionized electrically conductive plasma around the spacecraft? How do you envision the satellite would be protected from short circuits, metal whiskers, etc.?
Both good questions. With regards to electromagnetic interference, this is something that we do need to test in greater detail. We have not had the opportunity to do the industry standard tests that we would need to do to get the commercial clearance to use this. Anecdotally, and having $5 will buy you a beer down the pub. Anecdotally, I've had no trouble using computers, mobile phones, CB radios near the system while it's been operating. So it hasn't been noisy enough to interfere with any of these techs. It also hasn't done anything to FM or AM radio interference because you have the radio on in the lab, really. So short answer for EM interference is we don't know enough, but we think it'll be okay. As with regards to the cloud of ionized plasma, there kind of already is in one. Space isn't a pure vacuum, especially near the Earth and in low Earth orbit. There's a number of various species involved, various types of species in the plasma. Sorry, let me start that one again. There is already a space plasma at any altitude around the Earth where you'd be using this system. Most of it is moderately ionized air or oxygen depleted air, but there's already satellites and space stations already move through a plasma environment. This does need to be taken into account in their design because of spacecraft charging effects. They tend to collect a positive charge on their front face because the ions are moving slower than the spacecraft, so they tend to run into them. And the electrons in the space plasma are moving really quite quickly, so they collect electrons all over themselves. You need to be able to balance these charges out, otherwise you can get arcs and sparks and sadness.
Yeah.
The creation of metal whiskers, we get around in a couple of ways. Firstly, we're throwing the metal exhaust away really quickly. A specific impulse of 5,000 seconds corresponds to an exhaust velocity of about 50 kilometers per second. And delta V for solar escape from low Earth orbit is, please double check me on this one, I think it's somewhere around about 42 kilometers per second. So most of what we're throwing downrange is going fast enough, I think, to escape from the solar system. So we don't have to worry about it sticking around and forming metal whiskers unless it hits something. To get around the problem of it hitting something, we take advantage of the fact that our exhaust is actually fairly narrow. One of the ways of measuring divergence angle, the divergence of the exhaust plume, is the semi-conic angle. So if you've got your exhaust vector normal like this, you'll have your semi-conic angle out like that. And Hall effect thrusters tend to have semi-conic angles of about 45 degrees. So you get quite a wide plume coming out of them. Ion drives, such as gridded ion drives, tend to be closer to about 10 or 15 degrees semi-conic angle. And I've had published some results indicating that our thruster plume divergence, is about the same amount, 15, 17 degrees in that sort of ballpark.
Now, you've only tested this system in the lab. Have you been able to test it in any sort of vacuum chambers?
Oh, yes. It needs a hard vacuum in order to work.
Okay.
I don't run it, you can run it reliably when you're at 10 to the minus 3 millibars. I tend to run it more reliably down below 5 by 10 to the minus 5 millibar. 1 millibar is 1,000th of an atmosphere, so we're talking quite low pressures. I believe the static pressure at an altitude of about 350 kilometers is roughly 10 to the minus 6 millibars. So it has to, in order for us to do our experimental tests, we put it into an environment that replicates some of the conditions in space. It doesn't replicate radiation environment or thermal environment or atomic oxygen content, but pressure, we have to put it under low pressure in order for it to work.
Well, one question that I do have then is, obviously the next step would be to want to try, well, maybe not the next step for you in sequence, but the next big step would be to test this system in space. And you guys have a partnership with Airbus to facilitate use on the Bartolomeo platform that's going to be installed at the space station. And it seems to me that you guys are using that program, you're calling it FAST, the Facility for Australian Space Testing, to help the Australian space industry. But are you planning on using that capacity yourself to test this system?
We are indeed. In fact, that was our main reason for doing this because, well, I'm Australian. The traditional way that new interesting cool space technology gets developed and then verified is someone comes up with a great idea, they get the attention of the National Space Agency, something gets developed over the course of 5 to 10 years, and then it gets orbited as part of a demonstration mission or as a hosted payload on the space station, or back in the old days, used to be up on the space shuttle. Now, I'm Australian, and my nation doesn't have a space agency yet. It's pretty promising that we'll get one in the next couple of months, which will be lovely, but a couple of years back, this wasn't even a rumor that might have been going around the back end of Canberra. So when we decided to try and commercialize this, the question that we would have to answer is, okay, we're going to need to test this in space. We can test it on the ground all we like, but until it's flown, no one's going to really want to use it. To do this space testing, we looked at various options. Can we do a CubeSat version? How much do small demonstration satellites cost? Can we try and catch a ride with somebody else? And then we met the people doing the Bartolomeo program at Airbus in Bremen, specifically Christian Steinler, the project manager, and had a bit of a chat and asked, look, we don't think we're going to need all of that mass, but for our own purposes, is it okay if we do a bulk buy and get other people to fill it in? He was fine with that, and away we went.
Wonderful. That's great. I'm very excited to look forward to more of those results, and especially the type of ways that you can, I really hope that you'll be able to get this system off the ground and testing it out, but also the ways that you can help to enable the Australian space industry. And I've also noticed that there is quite a few things that you're doing to help out university students as well. So I don't want to take up all of your time today, but I do find all of this very interesting. And where can people find out more information about this project and the other different ways that you're trying to help the Australian space industry?
Well, there's a couple of ways. There's the website we should probably get cracking and do some more content on. That'll be at neumannspace.com. You can also find us on Facebook. We've got a Twitter account as well, as is de rigueur in these modern days. We also have presence at a couple of conferences around the place. Anyone in Adelaide who finds themselves on a loose end on Thursday, it's every 6 months the South Australian Space Forum is on, and the next one's on next week. I found it being a National Manufacturing Week in Sydney in May, and also a couple of conferences later on in the year, a couple in May in Los Angeles, and I hope to be at the International Astronautical Congress in Bremen this year. If you're there and you see me, come along, say good day. We can have a chat, no worries. Otherwise, drop us a line via the Contact Us section on the webpage, and yeah, we'll go from there, no worries.
Wonderful. Well, before I let you go, I do have a few more questions that we like to ask all of our guests, and just want you to answer honestly about these. The first question that I have for you is, what is your favorite space mission, past, present, or future?
Oh boy. Yeah, that's a toughie. Gonna have to say Mars Science Laboratory. That will be the Curiosity rover, on account of the Sky Crane was a beautiful idea and wonderfully executed as well.
Awesome.
Just a propulsion person from way back, and part of the problem with going really fast is you got to slow down somehow, and they did a novel little solution, and it worked beautifully. Yeah.
Another question I have is human or robotic exploration of the cosmos?
Both of them are good at different things. The great thing about robots is you don't have to feed water or air them. The crap thing about robots is they're really bad at doing things they're not designed to do. So there comes a point in time where you've done all the things that your robot can do, and you either need a new robot or you're up the creek. If you send some people there after spending all the time and effort to make sure they get there alive, and they'll probably want to come back as well. Once they're there, though, they can use all the human ingenuity they can bring to the problem to do new things, solve new problems, and have a go.
Where do you think that we should go next?
I think we should keep the ISS because it's a great technology testbed to test especially the biological sciences that we will need for further exploration out and about. Next step for human exploration should probably be the take it slow, take it steady way of trying some longer duration things further away from support. So the NASA plans for orbiting the moon with a crewed habitat, going straight to Mars in one fell swoop. A bit leery about that because I don't know how good the life support systems are going to be, especially how good they are closing the loop for over 9 months in travel, and then however long it takes for you to set up your air mining and chemical industry on Mars. So I'm thinking lunar orbit for crewed exploration, for robotic exploration. I kind of like the idea of a lot of the asteroid mining startups for doing some small 6-unit CubeSats to go off and have a look at more near-Earth asteroids from close up to do some remote sensing and prospecting missions.
Interesting, very cool. Well, my final question for you is why space?
Why space? Space speaks to a lot of people because we as human beings are explorers. We are endurance predators. We will go hunting by walking after things until they drop down from exhaustion. This has given us a pressure towards going out and seeing new things, finding out what's over the hill. This is something that we as a species do and that we are very good at, and it's why you will find humanity in a really, really broad range of habitats around the planet. Space is the next step. To go out into where there is even less ability to support, even less of an ecosystem to support people, to go that next step, to broaden our horizons, to make ourselves an interplanetary species so that we can move into more of the cosmos, do more cool things, find out more interesting things. And should something terrible happen to Earth, we don't have all of our species' eggs in one basket.
Well, very interesting. I agree with that, and I hope that these things are able to move forward and we are able to explore the cosmos and go out like that. So I like this very much. Thank you very much for joining us today. And to find out more information, visit newmanspace.com. Check out their Twitter, Facebook, YouTube. They've got a couple of videos. And be sure to join us in just a few minutes. We're going to take a quick break, and then we will be back with comments and questions from last week's show. Stay tuned. We'll be right back.
Science. It both draws us together and tears us apart, brings discoveries to cure us and threaten us. It is neither good nor evil. It is what we decide to make of it. There is so much more to learn, and we are curious. Together, let's explore the science of tomorrow.
And welcome back. Before we get started with your comments and questions from last week's show, we did want to give a huge shout out to the citizens of tomorrow. These are our Escape Velocity citizens who've been contributing $10 per episode on Patreon or $30 a month on makersupport.com. We also have our Orbital citizens who've been contributing $5 per episode on Patreon or $15 a month on Maker Support. But we also have our suborbital citizens who've been contributing $2.50 per episode on Patreon or $5 a month on makersupport.com. They get their name in the show during the third segment, access to our exclusive citizen-only hangouts, early access to After Dark, as well as free U.S. shipping in the Tomorrow Swag store. That is not worldwide shipping, so be close attention to that one there. Anyway, thank you so much to everyone who has contributed and making all of this possible. So, last week, we had a really interesting roundtable discussion talking about what is currently holding back humanity from our next big cosmic steps. And there were quite a few interesting comments that were made. The first comment comes off of YouTube from Addictland. And they say that there is a will among some people to colonize Mars, but there's no current way for them to do it. What we need is not the will to go for an extreme amount of money, but a way for it to be affordable or even profitable, since the will never be there for another Apollo-like infinite funding project. Elon Musk did not start SpaceX to create the will to go, even though he got it anyway to his surprise, but a way to go for enough people for it to work. And if he can really launch the BFR with 150 tons or 150 people or 100 people for $5 million per launch, as he recently claimed, he just might pull it off. What do you guys think?
I think making space more accessible for people by making it more affordable that's the number one thing that's going to change the way we become a spacefaring species. So I 100% agree with that. But I mean, Elon has to pull it off. I mean, that's the issue, right? Yeah,
it feels almost like an advocation of if you build it, they will come, you know, kind of attitude towards it. And I'm not sure if that's an actual thing because, you know, Falcon 1 was built and nobody really came for customers, if you will, on that. So we'll see. You got to do it. You got to bend the metal. You got to fly the thing, and you got to see what it's actually going to do. So that's what the future's for, to figure that out.
But even beyond what SpaceX is doing, I agree with Addictland here that we'd have to make a way for it to be profitable so that so much more organizations and just entities can get involved with stuff. But yeah, that's a big one, I think, that's holding us back. Anyway, our next question that also comes off of YouTube from Little Cripple. They said, I don't think money or even people's attitudes are holding us back like most people seem to. I think it's just time, science, technology, and reality. Like perhaps it'll never be possible to make space travel affordable for the common man. The resources needed to get just one of us off the Earth are just that great, or maybe we could. One thing I know is that we can't just skip into the technology of the future either. Humans are only so smart. We can only advance so fast. And as cool as us space nerds may think space is, so many people couldn't care and will never care. And what they want matters too. So we can't just divert a whole lot of their resources for our wants. So yeah,
that is a wall of text.
That is a wall of text, I know, and I know how we hate walls of text here, but that is a really good point that I think they bring up about, you know, we think about our Star Trek future is what I like to call it, you know, of having all these exotic technologies to be able to do this stuff, and what steps it'll take to get us in between where we want to go and be having colonies on other planets and where we are right now. And, you know, do you think that there is any potential way for us to go through the different transitions that we need to get from chemical rockets to something more exotic, or just to, you know, have the type of goals that we want?
So are you saying that, like, I mean, we have what we have now, and then we have this optimistic view of the future, but we don't have the steps in between? I mean, is that where, like, you know, the in-depth studies that NASA does, like, you know, there was like the Mars design reference architecture, stuff like that. I mean, we have those kind of steps, but then after Mars, we don't really have the next step and the next step and the next step after that. But we don't know what we're going to invent in 5-10 years' time. You know, Neumann Drive, that could become a thing that helps everybody to access space. So if we try and make those steps up now, we could be completely imagining the wrong track because we just don't know what is capable in the next few years. So are we wasting our resources if we try and think of those steps now, or is it better to focus on those closer goals and then hope that those closer goals lead us to the future, the vision of the future that we want?
I think there's like incremental steps that happen with things. Like it's very rare for you to have like something drop down and it just kind of changes everything. Like that's the exception, not the rule, kind of in how it works. I think that kind of leads into your next comment a little bit, Mike. I didn't want to steal the thunder for that.
No, I think so. No. You're absolutely right, though. But this next question or comment also comes off of YouTube from Stephen Thompson, who says, I think there's a misconception that our next steps will be giant leaps that will directly impact the majority of humanity. Really, there will be struggling small steps that most people will never hear of. In a decade or so, people will have space internet, but they'll think of the space aspect of it just as much as they do when they're currently using GPS. And when there's some big event like Starman, it'll be news for a couple of days and then fade away. So, yeah, I I agree with that. I think I love reminding people how much of what we've done in the space industry they use in their daily lives. And
yeah, and there's going to be, as we always try to note, there's always going to be a lot more failures on the road to success than just straight success. Very rarely is getting something actually done, a straight line, getting straight to it. Usually there's a branch out, and then you go, oh, well, that didn't work, and you come back to what you're working on, and then you take another branch. Oh, that worked. Oh, well, no, okay. And it's kind of like a tree heading up to get to the leaves, if you will. There's no real straight way to get there. And yeah, I think we have to remember that, and we have to understand that these are not things that are, at least at present, that we can just walk into and work with, because physics in general does not care what you want for the future. It simply cares about making sure that you follow its laws and rules, and that's a particularly big challenge for doing a lot of the things that people want for the future that people like us want to end up seeing enabled. So yeah, it's tough, but it's worth it.
I think that's why it's so important to talk about the latest advancements in space and what's going on, and do space news and a lot of kind of space science communication, telling people the new advances that we're having and how that's making the world a better place. Because if we don't talk about it, people aren't going to know, which is why this show is so important. It's why I like doing Tomorrow's Science as well. You have to communicate that out to everybody and make it as easily digestible as possible so that they can get excited about it too.
Mm-hmm.
Yeah.
So.
And I think things are getting better and better on that front all the time, and it's becoming more accessible all the time to everyone.
Yeah.
Yeah. Well, this next comment actually has to do with the launches from last week, and I thought this was really interesting, so I wanted to include this. This comes from off of YouTube from Shubhankar Chaudhary, and he says that the ISRO's engine, ISRO, the Indian Space Research Organization, VCAS is pronounced as VCAS, similar instead of VICAS, how we've been saying it. Mm-hmm. Similar to how you pronounce TCAS from the Air Traffic Collision Avoidance System. The name VCAS means development in our language, in Hindi.
Oh,
so
cool.
yeah, I didn't even know what the name of that meant. So that makes a lot of sense. Like, oh, it's the development engine. That's cool.
That's really neat.
Now we know how to properly pronounce it, and we will stick to that from now on, right, guys?
Yeah, sounds good to us. So we'll make it happen. Yeah, and that's
VCAS.
I really appreciate that from the community of tomorrow. Is that if we get something wrong, they don't have a problem correcting us.
Yep,
and,
definitely.
Yeah. And I know, at least myself, I don't have a problem being wrong as long as I'm corrected.
Yeah.
Because I like correction. It's good. It's good to know when we say something incorrect. To help us out, because we're not like the best at pronouncing things. So America,
yeah, especially with especially with all the different programs going on worldwide. I always think it's best to get it from a native speaker.
Yes.
Yeah.
It's more inclusive that way, I think, too.
Mm-hmm. Yeah.
Now, our last comment also comes off of YouTube. This is from MacFungo, or MacFugo, depending on how you want to pronounce that. And he says, with SpaceX changing the game, what we should be saying now is, this type of rocket has flown 4 times. Gets me momentarily excited about widespread reusability otherwise. Also, I think this is the first time I commented to you guys, so let me just add that you are the best thing on YouTube, in my humble opinion. Thank you very much, MacFugo.
Thanks.
Yeah, that's so nice of you. Thank you.
Let everybody know about us.
That's the best thing that you can do. But
right?
yeah. I think that it's pretty crazy too how we can say things like that. Like, oh yeah, this particular rocket's flown like 4 times. We couldn't say that just 2 years ago. That's insane.
That does kind of blow
me.
my mind a little bit.
Yeah.
And how we're just like, oh yeah, you know.
Yeah, well, you know.
No big deal.
Just
oh, they didn't land. They didn't reuse the one this time.
And people get angry about that, but like a few years ago, like no one was doing that.
Yeah, no one would have done that.
Calm down, internet. It's gonna be okay.
Yeah, I remember when that first the Vine came out from SpaceX showing the attempted landing on the barge at night, and it like came in like this, and it kaboomed, and everybody was like, "That's cute."
Yeah.
So good luck with that. And then like you know, nowadays we're like, yeah. Yeah, cool. 2 at once. Yeah, awesome. So
things are definitely getting exciting.
Yeah,
sure.
it is. I'm definitely good for it. So.
Well, that was all the comments and questions from last week's show that we wanted to talk about. But before we end here, we did want to give a really big shout out to our ground support citizens. These folks have been contributing $1 per episode on Patreon or $1 a month on makersupport.com. And they get their name in the final segment of the show and access to the citizen-only hangouts and early access to After Dark. And we just are eternally grateful to each and every one of you who are making this possible. And hopefully it just blows my mind how many of you are there. So I'm going to delay here just a little bit so that hopefully you get a second there to find out your name on the screen. And just it just amazes me how all of us together are making this possible, and that the type of messages that we're trying to put out there is possible because of you guys. So thank you so much to each and every one of you. For those of you who are watching live, After Dark is up next. For those of you who are watching on YouTube, that will be posted in about a month or so, unless, of course, you are one of our citizens of tomorrow. And if you are interested in becoming one of the citizens of tomorrow, you can visit us at patreon.com/TMRO or makersupport.com/TMRO to find out more information and become a part of the future. So thank you very much for watching.
And who have we got on next week, Mike?
Who have we got on for next week? We have Rod Pyle, who is going to be, oh my gosh, this is going to for exciting.
I'm so excited.
Yes. This is going to be really exciting. He's going to, he is in general engagement of the public for a lot of the grassroots support for the exploration and settlement of space. And the big conference for that a lot of you are familiar with is the ISDC conference, which is done by the National Space Society. So we're going to be talking about that, which is going to be held here in Los Angeles this year.
I'm really hoping that I get to go.
Yeah, that's going to be amazing. Yeah, for sure. So yeah, we're going to have Rod Pyle on next week to talk about that and get all of us pretty excited about that. That's going to be a lot of fun. Thank you very much. But yeah, thank you again for watching. After Dark is up next, and thank you for joining us. We'll see you guys next week.
Bye.
Bye-bye.